So it's my pleasure to introduce first speaker, Kristina Matovic. She will talk about some differential privacy concepts in time series analysis. So Kristina, the floor is yours.
Hello, can you hear me?
Yes.
Oh, okay, so perfect. I will now share my presentation. Can you see the presentation?
Yes.
Okay, perfect. So hello to everyone. I'm Kristina Matovic, a PhD student at the Faculty of Mathematics in Belgrade, and I work as a researcher at Vlatacom Technology in Abu Dhabi. I'm happy to be here and to have this opportunity to present our work to all of you. Our topic today is differential privacy in time series, balancing data protection and statistical relevance. Advancement of modern technologies have resulted in a large amount of data that is being generated, and we can use it for different researches or to create different relevant statistics. For example, we can use this data to make some statistical correlations, for example, for linking genotype, phenotype, or for identifying some risk factors with some possible outcomes. Then we have aggregate statistics, for example, traffic monitoring or smart metering system. I highlighted this part because our research it was a part, so we will use part of this aggregate statistic, like one of these examples for that. It is called counting time series. Then we have outlier detection, where we can, for example, detect intrusions or track disease outbreaks. Then we have data mining that has, for example, application in creating recommendation engine. But when it comes to publication of these data, the biggest challenge is that these data contain some personal and confidential information that we want to hide in some way. So while we want to get the most out of this analysis, we also need to ensure that everyone's data here is private. On the other hand, simply adding some noise on this data, it would make it privatized, but we are not sure if we can make that some useful statistics of that data. So the idea is to try to privatize the data, but in that way that we can have some big utility for the data that we are using after that privatization. So the concept that we will introduce today is called differential privacy. It was first introduced by Dwork in 2006, but it has some earlier roots in the researches of Warner in 1965. The whole idea behind this differential privacy is that we want to perturbate data in such a way that it keeps everyone's identity safe. So as you can see here in this sentence, it says that everything that you can learn with my help, you can learn without my help as well. This means that, for example, if we have someone's data in a database and we are using that to make some decisions, we will make the same decision even if some person is in this database or not. Now we will try to formulate some mathematical definition for the differential privacy. It says that some epsilon differential algorithm is epsilon differentially private if for all databases D1 and D2 that are neighboring databases, that means that they differ in only one single output. And for all outcomes in the range of that mechanism A, we have this inequality. It says that probability that the outcome will be in S if we use the database D1 is multiplicatively similar to probability that this outcome will be in S if we use database D2. As you can see here in this figure, the idea is that all outcomes will occur with almost the same probability if some person is in database or it is not in database, or if I supplied real or fake information. So we can define differential privacy as the probability being bounded by this value of epsilon. So before we try to apply some differentially private mechanisms or on time series. There are like some important properties of differential privacy. It is called group privacy, composability, and robustness to post-processing. Group privacy means that, for example, if we have T instances of some time series, and for example, one of these instances is the epsilon differentially private, then the time series will be epsilon times T differentially private. Then we have composability. Composability tells us that, for example, we can apply more differentially private mechanisms on the database, but that means that maybe we will use the whole amount of the privacy budget that we allocated for that data, and we will degrade the privacy that we have. For example, here we use the mechanism M2 with the privacy budget epsilon 1, mechanism M2 with privacy budget epsilon 2, and mechanism M3 with privacy budget epsilon 3. But combining these three mechanisms, we use the whole privacy budget that we allocated for this data. Then we have robustness to post-processing. This means that, for example, if we made some database differentially private, every operation that we will do on this data after that operation this won't compromise the privacy that we achieved with this data if we use these differentially privatized data. Then we have data sensitivity. It is defined as maximum amount of statistical information that can be affected by any single user. This is exactly what we are trying to hide with differential privacy, that difference that is affected by some user. So if we have that measure, if we have the measure on sensitivity, we could use that to understand how much noise we need to add to this data in order to be privatized. Then we will try to apply some different differential private algorithms on counting time series. Counting time series, they count different events or occurrences that are happening over time. And this sensitivity for this type of time series is at most 1. It is like 1 always, because, for example, if we have someone in a database and the value is 100, if that user opts out of the database, for example, here is like different, but the same thing, the result can be, for example, 99 or 100. So that means that it can differ by at most 1. There are different levels of differential privacy for time series. We have event level, user level, and W event level. Event level, it protects only single user movement or single instance, not the whole time series. Then we have user level. User level protects whole time series or protects the user movement through time, over time. And we have W event level that protects user movement that lasts at most W timestamps, like we are using some sliding windows that we are trying to privatize. So our aim here is to try to differentially privatize time series with epsilon privacy budget at user level by maintaining high utility. That means basically row relative error. We will conduct this experiment on 2 time series that have different characteristics in order to evaluate the performance of these differentially private mechanisms that we will use. First time series presents the total number of confirmed targets that are detected by the over-the-horizon radar. And the second time series represents the monthly employment rate for men. And you can see here that they differ in number of instances, in the range of values, and they vary in different dynamic properties. The first mechanism that we will apply on this time series is called Laplace perturbation algorithm. This is a main algorithm, differentially private algorithm. It was first introduced by Dwork. And the whole idea here is to add the Laplace noise to each timestamp of this time series X. So this scale parameter of the Laplace noise depends on sensitivity of this output function F, on the privacy budget epsilon, and of number of instances T. Privacy budget will be 1 throughout this presentation, and this sensitivity is 1, as we said, sensitivity is 1 for for each instance of counting series. And here you can see the results. For the first time series, the perturbation error is very high, and we cannot make some relevant statistics using this privatized time series. For the second time series, we have noisy data, but we maintain the trend, so we can make some statistics from this, because here the aggregation group size was bigger, and the impact of this noise that we are adding is less than in the first case. Then we have Fourier perturbation algorithm. This algorithm transforms data from a time domain to the frequency domain because it is based on a discrete Fourier transform. So we are trying to transform these time series, as you can see in these pictures, using this formula, so we can get the frequency spectrum. Here is the normalized frequency spectrum. And with that, we want to decrease the scale parameter of the Laplace noise that we are adding by reducing this sensitivity, and we can do that by creating this new time series in the frequency domain that for the first K instances have the first K Fourier coefficients that we calculated, and all the other instances are set to 0. And it is important to note that selection of this parameter K needs to be differentially private. After this, we need to apply Laplace perturbation mechanism that we defined before to these coefficients, but only to these first K coefficients. And this is the way to reduce this perturbation error, because we are decreasing this scale parameter of the Laplace noise, as you can see. And after we privatize the data in this way, we are trying to transform this data again from the frequency domain to the time domain, so we can have now the privatized data that we need. Here you can see the pictures, and now the perturbation error is smaller in this case, but again, we cannot make some good statistics from this, because this curve doesn't follow the curve of the original time series. And for the second, we have less noisy data, but for example, trend is not maintained. But for this second time series, the idea and the suggestion is to try to use the larger value for the K parameter, because the outcome depends on the choice of parameter K. For example, here I used the same parameter as I used in the first time series, but for this second time series, it is maybe better to use the bigger. So because here the aggregation group size is bigger than in the first time series. Doing research regarding this FPA algorithm, we found that there are some issues with this mechanism that can be improved in order to get less perturbation error. The main observation that we found is that real valued time series exhibit conjugate symmetry in the frequency domain that is called Hermitean symmetry. And our idea, because of that, is to try to privatize only the left side of the spectrum, or maybe you can privatize right side, it doesn't matter. So we will try to privatize this only one side of the spectrum by using the same algorithm that was proposed. But after the privatization is done, then we will try to mirror that side to the other side of the spectrum. In that way, we will decrease the scale parameter of the noise that we are adding, and also we will preserve the dynamics of the original time series in the frequency domain. So when we do the inverse Fourier transform, we will again preserve the dynamics of the original time series, and with that we will have the less perturbation error. And additionally, we are also just suggesting using of the first K maximum coefficients, not only the first K coefficients, then the first K maximum coefficients, because this will much better describe the original time series, and we will have the less perturbation error. And now you can see the results, and you can see that this yellow privatized curve now follows better the original curve, and now we can make useful statistics from this privatized data. And the same thing is here. So for the conclusion, so we try to apply different differential private mechanisms on this data, and we saw that the mechanism that is based on DFT outputs LPA mechanism in concept on preserving the stability. And also we proposed improved MPA algorithm that gives a better result in concept of balancing privacy and utility. And we found that utility of differential privacy data is closely tied to aggregate group size. And our future work will be concentrated on privacy budget allocation, frequency-based variable privacy budget, and application of Evlitz differential privacy. It is a list of literature, and that's it. Thank you for your attention.
Thank you, Christina. If there are any quick questions? If not, I invite you to write directly Christina, and we can now pass to the next speaker, Petra Laketa. She will talk about some depth functions. So, Petra.
Yes, okay. You hear me?
Yes.
Okay. Found the share button in just a second. Okay, so do you see the presentation?
Yes, I can see.
Okay, all good. So I'm Petra Laketa. I'm currently working as data scientist at Nordius on some A/B testing methodology. But what I'm going to present to you today is something the research I've done during my postdoc at Charles University in Prague. So the topic that I will be talking about is the half-space depth, and it's somehow between statistics and geometry in some way. I will explain how, but my idea for today is not to go deep into anything, just to somehow illustrate what it is and why does it matter. Okay, so the problem, as all of you know, on the line, we know perfectly how to order points, and we have defined quantiles, and it all works pretty well. But once we go into higher dimension, even in the plane, we are not sure how we would order points. What does it mean for a point to be more central than the other points? So imagine you have a sample in a plane, and you want to understand which points are more central. So it's not very clear how we do that. And there are many ways to approach this, but there's no like unique notion of multivariate quantile in general. And I will be talking about half-space depth, which is, by opinion of some people, the best approach for it, but that's up to discussion. So the half-space or Tukey depth was introduced by Tukey. And as I said, it's supposed to measure how central is given point. So in case of empirical measure, it's with respect to given data points and with respect to some general finite Borel measure. It's defined in terms of that measure. I will say later how exactly. So let's try with some example. We have 3 data points. Let's say each of them has weight 1/3. So then I want to understand what is the half-space depth. So what it will be the minimal portion of the sample points that I can cut off by a hyperplane that passes through given point. So here with this X, I denoted the point that I consider, and I want to see what is its half-space depth. So I consider all the half spaces or all the hyperplanes that pass through this point. And I see that here there is one half space that contains no points. So I know that the half space depth
for
of this point.
you.
Yes.
Sorry, we cannot see that you are moving yours.
Aha, you cannot see the cursor. Okay. So I will just explain, but you see on the picture that there is this
we don't
X.
see anything,
yes.
just the title page.
Oh, really? Okay. So I don't know why is that. Maybe to share somehow differently. Let me try
Maybe you can download the presentation and then.
Maybe in this way, if I share entire screen. Do you see it now?
Now we can see.
Okay,
yes.
Okay. So this was the title. Then I was talking about the problem and what is the half space depth, and then I came to this picture. So do you see cursor where I'm pointing out?
Yes, we can see.
Okay, great. Thank you. So I was saying about this point that we can see that there is a half space that has no data points. So its probability or its mass is equal to 0. So the half space depth of this point would be 0. If we take some point inside the triangle, then we can never find such half space. So every half space that we consider must contain at least one point, meaning that the half space depth of this point will be 1/3. And that will be for any point inside the triangle and also for every point on the boundary of this triangle. So we get something like this. We get a region here, a triangle with half space depth equal to 1/3, and the half space depth outside of the triangle is equal to 0. So that's a simple example, but how does it generalize? So if we have some finite Borel measure mu, then the half space depth would be defined as infimum of all mu masses of all the half spaces whose boundary passes through a given point. And given that, so the half space depth is a function, and if we consider level sets of that function, we get central regions. So central region of measure mu at level alpha is the set of all points in that Euclidean d-dimensional space that have the half space depth at least alpha. And these regions, they are nested convex sets. So the deeper point is, meaning the bigger alpha is, the smaller the central region is. So if we have, let's say, alpha and beta, and alpha is bigger than beta, then central region of alpha will be inside of central region of beta. So in that way, they are nested and they are convex sets. So and they can be expressed as an intersection of closed half spaces. And because of that, actually, the convex geometry plays a role into it. And there is a notion of something called floating bodies. And there were a lot of results that were used actually in the half space depth theory that were just derived from the results known in geometry, for example, for floating bodies. And floating body is, let's say, if you have in physics some body and you have water, so you let the body float in water, and there is always one part of the body that stays outside of the water. So if you would be rotating the body, you would be getting some region inside that body, and there is analogy between that region and the central regions defined for the half space depth. And because I was talking about quantiles, and of course we must think about the median. How is median defined? Well, we take the supremum of all values that have non-empty central regions, and then the central region for such supremum is actually median set. So I will illustrate here on some example. Again, empirical measure, I have 5 data points. And we can see that if we are outside of the convex hull of data points, we can always find a half space that contains no data points. So the half space depth would be equal to 0. But if we are inside, if we are in this region here, but not in the most central one, then we can always cut off only one point. So we have a half space depth equal to 1/5. But inside the most central pentagon, we can't cut off only one point. We always cut at least 2 of them. So the half space depth here is equal to 2/5. and that is actually our median set in this case. So another important thing is that for general measures, these central regions, they can look anyhow. We just know that they are convex. But for empirical measures and in more general for atomic measures, they are always polytopes, convex polytopes. And we know that every atom of atomic measure is actually a vertex of some central region, but the other way is not true. So if we have a vertex of a central region, for example, here we see pentagon and all the vertices, none of them is an atom. So the converse is not true. Another interesting term is minimizing half-space. So if there exists a half-space for which the infimum is attained. So as we said, the half-space depth is defined as infimum of mu masses of half-spaces, so that infimum doesn't have to be attained. But in case it is, we call such half-space minimizing half-space. And for empirical measures, minimizing half-space always exists because we have finitely many half-spaces with different probabilities. And that's actually used in a lot of proofs for empirical measures, and that can be generalized to something called like half spaces for more general measures. And then I will just mention some paper that we've done in 2021. So the thing is that for atomic measures, it's possible to fully reconstruct atomic measure based on its half-space depth function. So if in the whole space, we know what's the value of the half-space depth at any point, we can trace back where are the atoms and what are their masses. So how we do it? Shortly, as I said, every atom is a vertex of a central region, but the other way is not true. So it's enough to make some algorithm that will go from the outside. So from the lowest level central region going towards inside, and we'll be checking each vertex. And we developed a way how to check every vertex and how to exactly compute its mass in case it is atom. But important is to note that half-space depth doesn't fully characterize general measures. So we cannot have such result for more general measure. We have this only for atomic measures. And yeah, here I've described shortly what is a reconstruction procedure, and we have in that paper some two procedures. One is exact but slower, and the other one is more approximate but is faster. So that's all I wanted to cover today. Thank you for attention.
Thank you for the very nice talk. Are there any questions? No, if not, we will keep going to the next presentation since we are very stuck with the time. So it's my pleasure to introduce our third speaker, Maria Cuparic, who is actually the organizer of this session. So Maria, the floor is yours.
Thank you. I am Maria Cuparic, and I am assistant professor at Faculty of Mathematics, University of Belgrade. And I will talk about goodness of fit testing for randomly right sensor data, actually about two approaches. This is my joint work with Bojana Milošević. In survival analysis, the focus of the study is usually on time until a certain event occurs. For example, if we consider survival time after some surgery, that is one event in survival analysis. The final goal of the study is to answer specific questions related to survival time. And the most common starting point is to choose appropriate distribution of the data and performing some goodness of fit testing. For example, if we have some ID sample, we want to test null hypothesis that distribution of that data belongs to some family F0 against alternative that it belongs to some other family. For complete data case, there are a lot of different goodness of fit tests, classical ones or tailor-made, but study is mostly time limited, and some person might leave the study for some reason. And in that case, we have randomly right censored data, and goodness of fit testing in that case is not there is no a lot of goodness of fit tests in that case. What is actually randomly right censored data? If we consider survival time after surgery in months, one patient can leave the study, or some other patient we can lose to follow up, or we need to stop considering some patients because of time limitation of the study. In each of these cases, we have some survival time, but also we know that time is not true survival time. In that case, we have actually n pairs as a sample, where first coordinate is minimum between two random variables from a non-negative continuous distribution functions f and g. And second coordinate is indicator of censoring, which is equal to 1 if element is not censored. We assume that the censoring model is independent. Actually, we assume even a stronger assumption that these two sequences are independent. In that case, if we consider goodness of fit testing, we can apply different approaches. First one is test adaptation, meaning that you need to adapt procedure for this kind of data. Although the first tests have been proposed in 20th century, until now, this field of research is still not well explored. There is some improvement lately in this problem. Second approach is data imputation, meaning that instead of using this censored part of data, you impute some other values in that places, and you use complete case analysis in that case. There are plenty missing data imputation algorithms, but most of them are for missing at random data. Only algorithm which we found in literature for censored data is proposed by Balakrishnan and co-authors in 2015. I will talk about it later. A third method is data amputation, meaning that you erase all censored elements and work with smaller sample size. Actually, this is a method which is often used in literature, especially in social sciences. And the last one is ignorance, meaning that you ignore information that there is censored elements in your data. And this method is actually some kind unpredictable. It can give good results, but we don't know when and why. I will talk a little bit more about test adaptation and data imputation. For test adaptation, we consider inverse probability censoring weight approach. First, we considering testing goodness of fit testing for exponential distribution, and we consider two classes of test statistic proposed lately. They are based on integral transformation and L2 transformation of U empirical process. Those processes are based on Laplace transformation and characterizations. Here we considered Puri-Rubin and Dessous characterization. For our adaptation, we actually need to adapt this empirical process, and then our test statistics will be obtained in the same way as in complete data case. For adaptation, inverse probability censoring weight approach, meaning that the original kernel is weighted with this weight function. This is actually product of indicator of censoring, and it's divided with probability that elements are not censored. Actually, that probability can be expressed as survival functions of censored element. But since that distribution is unknown, we need to estimate it. And here are the Kaplan-Meier estimator of that survival function. The asymptotic properties of our test statistics were obtained in our paper, and you can find it there. For small and moderate sample sizes, we need to use the bootstrap algorithm. Actually, some resampling method, but we use bootstrap algorithm, and this is bootstrap algorithm for composite hypothesis of exponentiality. I will not go into details. I will just emphasize that censored elements are generated from Kaplan-Meier distribution, and random variables from a sample from target random variables are obtained from null distribution with estimated parameter. For estimation, we used maximum likelihood estimation for randomly right censored data. This method is actually is also theoretically justified, and we use it in our empirical study. For data imputation, we consider two algorithms. First one, I already mentioned it. It's proposed by Balakrishan and co-authors in 2015. Its idea is to, for each censored element, you need to generate some element from uniform distribution in this interval, where F0 is null distribution. Then each censored element is replaced by inverse transformation of this element from step 1. You need to do that for each censored element, and then you can calculate test statistic based on this modified sample. In this case, it can be seen that this will give good results for empirical sizes, but for empirical powers, it depends on alternatives. Because of that, we try to find some improvement, and we consider this adaptation of first algorithm. Actually, we added step 1, where we first estimate the distribution of target random variables, that uncensored part, and then smoothed it. In first step, instead of using null distribution, we used this smooth approximation. All other steps are the same as previous. For smoothing, we consider two methods. First is monotone cubic spline based on uncensored elements and Kaplan-Meier estimator. Those lines are presented in green. And we consider Bezier estimator proposed by Kim and co-authors in 2003, which is based on Bezier curve. This Bezier curve is based on n+2 points, where first and last points are always known. Those curves are presented in red. First graph is related to null distribution, and Second graph is related to one alternative distribution, in this case, half normal. We can see here that black line, which is now distribution, and blue line, which is actually now distribution with estimated parameter, are very similar. But in case of alternatives, there is some division. If we consider a red line, the approximation is better in both cases, especially in alternative case. For green line, we can notice that this line is too crunchy, and also here the values are less than 0, which means that this is not survival function. Because of that, we consider Bezier estimator for our approach. And we consider a huge empirical study for moderate sample sizes and significant level of 5%. We consider simple and composite hypothesis of exponentiality for 15 alternative distributions and 7 test statistics. 4 of them are our test statistics. For obtaining certain censoring rate, we consider causal green model and a model where sensor distribution is a Lindley distribution. And we consider 4 approaches, actually 5, since we have 2 imputation algorithms. As competitors, we consider these 3 adaptation of some tests proposed for complete data case. First one is called Kramer-von Mises test, then test based on maximal correlation, and test based on properties decreasing mean time to failure class of life distribution. And before I proceed to results, I need to emphasize that we notice that our imputation algorithm is not well calibrated, meaning that if we consider 10% of censoring and significant level of 5%, for example, first test will have empirical size equal to 6. And that is not a huge problem, but if we have 30% of censoring, that empirical size is 8. Because of that, we try to consider some calibration method, meaning that for each test and each censoring rate, we will find significant level which will produce empirical size equal to 5. And then we will use that significant level for obtaining empirical powers. For example, for this test statistic, this is appropriate significant level is 4. And you can see it for all other tests. If we compare those 2 models for obtaining censoring rate, we can notice that there is no significant difference between appropriate significant levels. And here, just small part of the results. We can see that with bars are presented the results for causal green model, and with squares are presented the models for Lindley distribution. If we consider adaptation procedure as benchmark, we can notice that first imputation algorithm has always the smaller empirical powers than benchmark. Imputation algorithm 2 has almost the same or larger values than benchmark. And for imputation, we can notice that values are all smaller in almost all cases. Only exception is log normal distribution. In this case, ignoring mechanism has almost always a better result, but there is significant difference in that case for causal green model and Lindley model. If we compare these 2 different test statistics, we can see that our test statistic always has larger empirical powers. I will just give a brief summary. We can notice that imputation, if we consider all empirical study, we can notice that imputation algorithm 2 is the most stable, and also if is conducted with calibration, and it's much more convenient than adaptation procedure. Amputation and imputation algorithm can be used in some cases for composite hypothesis, but in case of simple hypothesis, they have very bad results. And some direction of future research, we want to consider different sensoring mechanism and also different imputation mechanism. We want to consider all these approaches for sensor data in the presence of immune units. Actually, we considered some adaptation method, but we didn't work with imputation. We still didn't work with imputation mechanism. Here are some references, and thank you for your attention.
Thank you. Thank you, Maria, for organizing this lovely session. And we come to the end. So the last talk is my talk. And now I will share screen. Okay. Okay. So as you can see, today I will talk about some testing problems, but not for classical data, but for some directional data, with highlighting some perspective for further adaptation to other spaces, with putting focus to non-Euclidean ones. So the results I'm going to present are part of our bilateral project with Karlsruhe Technology of Institute of Technology. And in particular, what I'm going to present is part of a joint work with Maria and Bruno Ebner from Karlsruhe Institute of Technology. And also, last part of the talk is related to some recent results obtained with my PhD student, Jelena Radojevic. So, as you all know, there is a bunch of tests for goodness of fit tests and independence tests for classical data. However, there are not so many that can be used also for other types of data. And by other types of data, I have in mind all data that are not classical numerical Euclidean data. So the main goal of this talk is to present some flexible independence tests that might be applied for different types of data, with putting special focus on testing independence among some directional data types. Here is one example. We can see some midpoints of known craters on the moon with diameters greater than 50 kilometers, and one can be interested in testing independence among those locations with some weather conditions and many others. So it's really important to provide some tools for that. However, in the literature, there are not many tests that can cope with those kind of data. The presented example was just one of this type, but there are many others. I have to mention that there are very well-known examples while looking for the wildfire orientation, usually very popular during the summer. So it is important to somehow model the dependence between those type of data and many other factors that are obviously of different types. What is important when a novel methodology is proposed is that the data topology is kept through some estimates that are proposed to measure location, variance, and any other measure. And here we can see that, for example, sample mean, if we take data from the circle and consider a sample mean, the sample mean will not lie on the circle. That is one typical example when we cannot envision some concepts proposed for Euclidean data to the case of circular data and many other data that are of directional types. So we need to somehow propose something else that works. And in our search for that, since we focus our previous research on independence tests for Euclidean data, we were looking for some measures that can be also applied for this kind of data. And we come to the very well-known so-called alpha energy distance, famous distance between two probability measures. one induced by vector x, one induced by vector y. It is important, due to simplicity, I put here that those vectors are of same dimension, but it is not necessary to assume that. We can also assume that the vectors are from spaces of different dimensions. That is very important feature of this distance. So, as usual, when independence tests are proposed, one can consider the distance between the underlying joint measure, probability measure, and induced measure by the product of the marginal. So, induced measure if we assume the independence of those vectors. And it leads us to the very well-known distance covariance function, which is given in this form. So it's an adaptation of already proposed measure. This coefficient A can be considered as a tuning parameter and can add additional flexibility to the underlying distance. What is important to note that this distance covariance can take any value, so we need somehow to standardize, and following the classical idea with the correlation coefficient, we come to the so-called distance correlation coefficient, which is very well known in among different types of statistical disciplines. So this is what already exists in the literature, and in some cases, those expressions have very suitable expressions when we consider different data types. So let us imagine that x lie on the circle. Any circular data can be expressed with two coordinates, but intrinsically it is just one angle, because we know that the norm of that observation is fixed. So basically, we can still apply Euclidean distance between those variables, but we have to take into account that the norm of those vectors are fixed. And luckily, this distance covariance allows us to account for this. So we were looking about this distance, and we were thinking, can we replace this distance function, so classical Euclidean distance to the power of a, to some other measures that can work in arbitrary spaces. And we come to generalized kernel-based distance covariance function, in which we can basically replace our previously presented function Ka with any negative definite kernel function. It can be shown that it is very well defined, and that some already shown properties hold, in a sense that we have the distance covariance equal to 0 if and only if x and y are independent vectors, and that is the crucial property of this distance, which enable us to consider the appropriate test. Of course, tests are considered as empirical analogs of those guys here. So any expectation can be replaced with the appropriate mean function, mean with respect to several variables. So we come easily to asymptotic properties by applying some theoretical result for V statistics that are the V statistics that are form of our resulted statistics. So why it is important to highlight this once again? So by changing those functions, a kernel function, we can add additional flexibility, but not just like that. We can also apply some other functions, and that is definitely one of directions for our future research, in a sense that we can consider, for example, the problem of testing independence among matrix data and Euclidean data, or matrix data and directional data, or any categorical data and directional data. So any combinations, because we can combine those functions in a way that we can use different functions K for different vectors. That is, I would say, the main feature of this distance. So in order to see how actually this works, we conducted very wide empirical study in which we consider testing independence and X and Y were of different types. So we consider testing independence when X is a circular random variable and Y as well, when both X and Y are spherical data. So we enlarge the intrinsic dimension of X and Y. And we also consider the mixtures when one component is circular type and one component is Euclidean one, so classical. This case is usually called the problem of testing circular linear independence. And we were a bit surprised when we started working in this area. There were not many competitors we can find in literature. Of course, there are a few in the case of testing independence in the most simple case, but for others, we couldn't find more than 1 or 2 competitors in the literature so far. So the goal of our study was to explore the flexibility of a test, but also the robustness with the selection of kernel function. So we wanted to see whether it is important or not to select kernel function properly, and we come up to conclusions that the choice of this kernel is very important. And that is one of the directions for future research, because we don't know in advance which kernel we should select. At this moment, we can propose some kernel functions that, let's say, that resulted in the most powerful test against the majority of alternatives, but in general, we do not have a general recommendations. Also, tests were very flexible. They work with different kind of data. They were easy to implement. That is a very important feature. There were some other tests in the literature, some of them based on density estimators, and they were much more computationally intensive. So from the practical point of view, I think this property is very important. And one of the applications of our methodology is definitely the problem of variable screening, the problem of reducing dimension of the underlying structure of the data. So there are many cases when we are dealing with the high-dimensional data, and by that I mean the cases when the number of underlying features, independent features, is much larger than the number of units. So there are different approaches how we can cope with those cases. However, all of those methods based on regularization requires not such a high discrepancy between those sample sizes. So in those cases, we need to do first something else and then to proceed with the regularization methodology. And while searching in the literature, we find how it can be done. And one of those methods is so-called marginal screening. So the idea is to first somehow reduce the number of underlying important features and then to apply one of very well-known regularization methods to obtain the final reduced set of important variables. And it was first proposed by Professor Pan, in which he considered in his work and with his co-author, they considered the case of sparse linear regression. So they gave some conditions, the conditions of sparsity, and their idea was to use a Pearson correlation coefficient to obtain the set of important predictors. So what they consider the correlation between y and x1, y and x2, y and x3, etc. And then they rank predictors based on the underlying correlation measure. And it turns out that this approach works rather well, in a sense that it can be shown that by doing like this, if we select in advance the number of predictors we are going to keep in the sample, that depends on n for sure, that we will select those true important predictors with a probability 1. So this property is called sure screening property. Why it is important? Because then later, if we want to use another methodology, we will start from the set that contains true active sets. So the crucial methodology that allow us to apply another variable selection procedure later. However, if there are no linear relations between data, Pearson correlation coefficient doesn't work at all. So we need something else. and naturally distance correlation is good choice. So what we did, we started with our generalized kernel-based distance correlation and applied it in this context. And this enabled us for the first time to look for the variable selection problems when one of the components is not Euclidean type, but for example, directional. And here you can see a model of this type. So there are many directions for future research. Now we don't have any, but if there are some suggestions and questions, please write me by email, or if you find another way to reach me out for this purpose. So thank you very much for listening my presentation.